a stats course that's a term long or more course. So it's definitely not covering all of that in detail. So we'll go into it a little bit, but not into a huge amount of detail. And I'm not going to touch that cord again. We'll give it a second to come back. Okay, is the audio working? It's going good? Okay, great. Okay, so in the email that was sent out, you were asked to install 3 packages. And I've actually, we're actually only going to use one of those. And I'm hoping that we'll actually use one other one. So we'll go through together installing 2 packages in R. And the way that we're going to do that is just install .packages. And we're going to install 2 different ones. So one is psych. Oops, I'm spelling it wrong. PSYCH. And the other one that we're going to install, this is the one that I hadn't mentioned before. It's called core plot, making correlation plots. So we need to install both of those. So once you type it, you can just click on run or hit Control Enter. We'll just give it a second to do that. And then we've just got to load each of them. So we'll do library, brackets, and then the package names again. So library site and library plot. And run those 2 lines. Okay. So there's lots of different sample data sets within R that you can use to demonstrate some of the things that we're going to be talking about today. But I couldn't find a good one to demonstrate some of the basics. So we're going to just create our own data set. It's going to be very small. So we'll be a little bit of typing in terms of typing in numbers as part of our data set. And just to give you a bit of an overview of what we'll be doing today. So we'll be talking about setting up your data so that you can run t-tests, which is where you're comparing the averages of 2 different groups or the means of 2 different groups. So that's where we're going to start with. Then we're going to talk about comparing the means of more than 2 different groups, which is Anova. And we'll talk a little bit about correlation and a little bit about regression. And so this is like a lot to kind of shove into 50 minutes. So it's really just going to be an overview. I know that actually one of my colleagues at the Map and Data Library, where I'm at in Robarts, is developing a couple of 3-hour workshops on stats in R right now. And so those are things that might be useful to look at next term if you want more detail than what we're going through today. All right, so basically we're going to create a couple of vectors of scores, and I'm being a little bit vague here, but the score could be, for example, a result from a medical test. It could be the score on an educational test. It could be the length of flowers. It could be the length of an animal's tail. It could be kind of anything that you're measuring related to your own discipline. So we're going to create 2 different vectors. One we're going to call group 1 score. And the numbers themselves aren't super important. I mean, I picked them kind of randomly, but it'll be helpful to have the same numbers just so that when we're looking at the results, we're looking at the same things together. So there's going to be 9 scores that we're going to put in. So that's 6, and then so that's our set of scores for our group 1. And then we're going to have group 2 that has another set of 9 scores. Okay, so as I said, I set these up fairly randomly, but it could represent, for example, group 1 could be medical result from patients of a certain age, and group 2 could be medical results from patients of a different age, so children versus adults. Or it could be one classroom that received a certain kind of educational intervention versus a classroom that received no educational intervention or a different kind of intervention. So maybe testing online versus in-person teaching, something like that. Okay, so we'll just run each of those lines just so that we add those 2 variables. So now we'll see them in our environment in our upper right-hand corner here. Because I'm zoomed in so much, it's a little bit big on my screen, but you should be able to see the values that you've just added in there. And so because now I have these 2 kind of sets of scores from 2 different groups, I want to create a data frame that brings all of them together. And this is something we're going to do by, we're just going to create a data frame called my data. And I basically want to create a data frame. So my data, and we're using what the kind of assigning code in R, which is the, less than sign and then the dash. So we want a data frame, and we're going to have two variables in the data frame. So the first one is going to be, and we want to indicate what group each of these scores were from. And so I feel like this is code that looks a little weird when you first type it, but it will hopefully make sense once we type it out. So we're going to have one variable called group. Yep. Yes. They're provided by the U of T coders. Please, please eat snacks. So we're going to have one variable that we're calling group. And basically, I just want to have a column that says group 1 or group 2 for each of these. So because I have these 9 group 1 scores in order, I can use the repeating command within R. And then I can use, so I used C up here as well. Because this lesson is assuming that you've done some R before, I guess I'm not going into details about everything, but C to define a set of scores that we want to combine here. And in this case, we're going to use C to say, we want to have the text group 1, and then the text group 2. And this is going to go off a little bit here. So we've got, I want to have the text group 1 repeated 9 times, and then the text group 2 repeated 9 times. And so this will hopefully make sense if it doesn't immediately when we look at the data in a second. So this is our group data, and then we need to have our score data. So our score data is just going to be basically the combination of those two vectors that we just created. So group 1 score, and R, of course, is good at kind of popping up and telling you what things you have that start with the letters you just typed. So you just hit tab, group 1 score, and then group 2 score, and hit tab. And you should have 2 closed round brackets at the end. I think mine jumped a little bit. Let me put one more in there. So if you run that line, okay, mine has unexpected symbol. So what have I done wrong? I think I forgot to put a closed bracket after group 2 here. So you can check if you also have that missing. So once I do run that line successfully, what I'm going to see in the upper right-hand corner here is that there's a data frame called my data. There's 18 observations. We have 9 observations from group 1 and 9 observations from group 2. And there's 2 different variables. So one variable is a factor level variable where it's either group 1 or group 2. And then the second variable is score with all the numbers. Is there anyone who does not have that? Okay. Were these 2 lines able to run? Were you able to run those 2 lines? Okay. You can take a look and see. Okay, great. Oh, sorry. Yes. If I open the data set, yeah. It doesn't make sense. It does or it doesn't? Okay, so let me take a look. So I'm just going to type my data and hit enter so I can see it. So does it look like this? Or no? Not like that? Okay. So I think there might be something that just got typed slightly. Yeah. So we're going to have my data and then assign it to data frame, data.frame. And then our first variable is group. And in that variable, we're going to repeat group 1 9 times and then group 2. Yeah, got it. Okay, so those who didn't have it before, you've got it now? Okay, great. And this is just setting up the data in a way that R likes to use it. Oops, there we go. So that we can run the tests kind of as they're set up, basically. So the library one of the libraries that we imported called Psych has a couple of functions that let you look at details about your data in a fairly easy way. And so one of the functions within it is called describe. So we can type in, for example, describe, and we can put in parentheses my data and then $ to say which particular variable we want to look at. And then we can either type or click on score. So if we run that line with enter or clicking on run, then what you should get in your console is a description of the entire 18 scores that we collected. So it's going to tell us how many scores there are, what the mean is, what the standard deviation is, and then a whole bunch of other kind of descriptive statistics that may be useful. Everyone seeing that? The other function that's useful or one of the other functions that's useful in Psych is describe by. And so you need a capital letter B in by. And so we're going to start in the same way that we did before by putting my data $ score. But this time we're going to tell it that we want it to divide it up by group. So we actually want to see what are the summary stats for group 1 and what are the summary stats for group 2. So we tell it first that this is what we want to see the data for, and then we tell it how we want it to divide it up, or what the groups are. So we have described by my data $ score, comma, my data $ group. And if we run that line, so it looks a little bit funny on mine just because of my zooming in, so I'll move it over a bit. But you'll see descriptive statistics for the two groups separately now. So you've got group 1. This can just kind of give you an overview to start with. So you're looking at group 1 has a mean of 51.56. So again, that could be centimeters or a test score. And group 2 has a mean of 68.67. And so we're working towards wanting to compare the means of those two groups. But this is a good start just to know what the means are, to get a sense of what kind of values are we looking at to begin with. All right. So how many people here have used a t-test before? Okay. So kind of just over half. So the t-test, or it's sometimes called the student's t-test, is something that you can use to compare the means of relatively small groups. So under 30 is kind of what the number is usually given, which often makes or can make sense in lots of different situations. In our case, we have these 9 data points for these two different groups, and we want to compare the means, so that's a good test to use. And there are a few assumptions that are in place if you're using that test. And so we need to check whether our data actually meets those assumptions, because the test will still run even if it doesn't meet the assumptions, but it means that the conditions that we're working with might not actually be valid to be able to run that test. And again, we're kind of glossing over this a little bit just in terms of wanting to be able to show the code and not getting into a lot of detail on the theory of it. And these are really some basic things to look for in your data, but often for the tests that we're looking at, you need kind of enough exposure to them to know for your discipline and for your area when they're used and what things to look out for. So the 3 big assumptions are, one is that the data is independent. And so that means that, so let's give a specific example in this case. So let's say we're looking at educational scores from 2 different classrooms. One classroom is kind of the baseline group 1, using the method that was used, that's always been used in that classroom. And then group 2 is using a new educational method. And these are the scores on a test that's been given to the classes afterwards. And so the data is independent, meaning that there's no connection between the students and the different classes. We're not looking at a student doing a test again, in which case that would be paired or would be connected to that student. We're looking at these 2 independent groups. So that's one thing that we would assess just by understanding our data. It's not like a statistical test, it's just a logical test, I guess we would say. Another thing to test is that your data is normally distributed. So normal distribution meaning kind of the bell curve shape for data. And there are tests that you can run to check if your data is normally distributed. You can also plot a histogram and take a look at your data, but that's kind of more of a, what would be the right word to say it? Like not a formal way to do it, I guess. That's kind of a way to see generally is my data normally distributed, but there's a statistical test that we can use to check that as well, called the Shapiro test. And so that's generally something that you want to do. If it's not normally distributed, there's other tests that you would do instead of the t-test. So for any example where there's a statistical test you can do when your data is normally distributed, there's an alternative test that you would do if your data is not normally distributed. So we will do this just for one part of our data set, just so I can show you. I can tell you that I ran this for both of them and they are normally distributed, both group 1 data and the group 2 data, but we'll do one of them together so that we know how to do it. So I mentioned it's called the Shapiro test. So it's literally Shapiro.test. And we can either, because we have these two vectors that we created at the start for group 1 score and group 2 score, we could just run the Shapiro test on group 1 score as is. So that should work. We do group 1 underscore score. It's not actually how I did it before, so let's try if this one will work. And so what you should get is the results of the Shapiro-Wilk normality test. And this is a test where your null hypothesis that you're stating is that the distribution of your data and there's no difference between the distribution of your data and a normally distributed data set. And so often when you think of p-values, which we'll talk about more in a minute, you think about wanting to see a low p-value, but in this case, a high p-value actually means that it is normal, because our null hypothesis is that the data is normally distributed. And so we have a high p-value, so we cannot reject that null hypothesis. So we're going with the hypothesis that the data is normally distributed. The code that I had used when I didn't have the data set up like this, or sorry, not when I didn't, but if I wanted to refer back to the my data frame, you'd have to use the kind of filtering functions within R in this case. And so I'll just show what that looks like. Feel free to type along if you wish, but it's basically doing the exact same thing as the previous line. And so that would be typing Shapiro test. And so I would be referring to my data and the score, but I would need to specify that I only want to look at the group, my data $ group. So in this case, I'm saying I'm only looking at group 1 because I want to look at group 1 and group 2 separately. So running this should give me the exact same thing as I got for the first one because it's using the same data. So it really depends on how your data is set up as to which one of these would make the most sense, but it'll do the same thing. Okay, so in this case, we've confirmed that our data is normally distributed. Another thing that we want to check is whether the variances are equal between the two different data sets, the two groups that we're working with. And similar to Shapiro test, there's a test called just var or var.test. And in this case, similar to, so with the Shapiro test, we're making the hypothesis that our data is identical to a normal distribution or not different from a normal distribution. In this case, our test we're running is saying that our variation of our first group is not different than the variation of our second group. And so we want to see whether or not that holds true. And so in this case, for the variation test, we type in first what's the variable that we want to test, so our score, and then we use the tilde sign, I think that's what it's called. So it should be to the left of your 1 key on your keyboard. And we say group, because we basically want to say for each of the 2 groups that we have. And then we say what our data is. So data equals my data. So when we run that, kind of similar to the first one, we see that we have a p-value here that's saying that we cannot reject our null hypothesis. So we can move forward with the idea that our variances are equal. It tells us what the ratio of the variances are. So it's actually saying that the variance of one of the groups is 2.8 times bigger than the variance of the other group. So it might seem like that's actually not equal between the two groups. But I think what I've generally heard or experienced is that if the ratio is 4 or less, that generally it will be seen as close enough, or yes, close enough that it's okay to assume that the variances are equal. So we looked at our first test, which was wanting to check whether our data is independent. That was just kind of our mental or logical test. And then we looked at these other two tests to check if it's normally distributed and if our variances are equal. And so now we can say, okay, we can run the t-test. We meet the conditions that are needed to set that up. And so as we're wanting to run our t-test, before we run it, we want to think about what our hypothesis is. And so our hypothesis in this case, generally you would state your null hypothesis is that that there is no difference in the means of these two groups, that the educational intervention in this case does not have an effect on our scores for our different groups, on the mean scores. And we also need to set what our value of alpha is. So alpha being the level that we're setting for confidence that we're willing to accept of how confident we are in the results of our study. And this is very much discipline based. In a lot of areas, you might see 0.05 set as the alpha level that we're going to compare our p-value to. But there's other areas where that wouldn't be considered acceptable, and you would be going to 0.0. So that's very much a disciplinary based thing to think about. There's also a lot of discussion in different communities, especially in psychology and statistics, about whether null hypothesis statistic testing is in fact the best way to approach looking at different groups and comparing them. So I definitely encourage you to read some of that literature. It's really interesting. And one thing that it really focuses on is, instead of looking at the situation as just kind of a pass-fail or a significant or not significant, is really looking at the magnitude of the differences or the magnitude of the results that you're getting. So we'll talk about that in a second when we see the results. But the idea being that something can be statistically significant, but not actually meaningfully significant in the real world. So you can find something where you can say that there's a statistically significant difference between two groups, but the actual difference in score, for example, maybe is 0.5 on a 100-point scale. And so just kind of thinking logically about, is this something we want to invest a lot of time and training into for teachers or for whatever group we're looking at, to realize a 0.5 change on a scale. So there's a lot of talk about how do we determine what is a reasonable difference? Like, is it, some kind of educational intervention that increases a score by 5 points? Is that a good thing? Or 10 points or 1 point? And that's really discipline specific, and it's really based on experience in a lot of cases. It's psychology is where I've seen the most discussion about it, especially in terms of looking at like psychological interventions and measuring like on a scale of anxiety or depression, kind of thinking about, does 2 points on a 9-point scale mean that a treatment has been very effective? What number do we need to see, as opposed to just saying there's a statistically significant difference, but someone's life might not actually feel different to them. So that's just kind of some caveats or things to think about first. Oh, I touched the cord again. We'll give it a second. So to run the t-test, so we want to compare the averages of our two groups, the means of our two groups. So it's fairly straightforward to type in. We just have t.test, and we write in the two different scores that we're comparing. And when I'm looking at what I wrote here, I put group 1 score and group 2 score in my notes. But the other way to do it would be looking back at our previous line when I did the Shapiro test. if you didn't start with those two different vectors, you just had one big data frame to start with, you need to type in something like what I'm highlighting here to be specific about which group it is that you're comparing to the other group. There's a few things that are defaults within the t-test. And so just before we type any more, I'm just going to show you if you're in the bottom right window of R, you can type in the help menu or the help screen here, the one with the magnifying glass, t.tests. And I won't go through it in detail, but it will show you what all the defaults are, as well as an explanation of what the different arguments are as well. And so it's important to know what the defaults are. So you can see, for example, that the default confidence level or alpha level is 0.95. The default that the two groups are paired is false. The default that the variances are equal is false. And so in this case, we need to look at which ones of these are true for our data and make sure that we can leave those ones as is, or we can be explicit and specify them. But we need to especially make sure to kind of correct the ones that are not actually true. And so we need to set here that our variances are equal. So var.equal equals true. Var.equal equals true. And we want to set that our alternative hypothesis is two-sided. And the options here are two-sided, less than, or greater than for your alternative hypothesis. So if your null hypothesis is that the two groups are not equal, the two groups have unequal means, then your alternative will be two-sided. You may also have a null hypothesis that one group is less than the other group, or one group is more than the other group, and then your alternative would be less or greater. I'm not going to put things like the confidence level because they have it set the default at 0.95, and I've decided I'm good with that. My alpha is 0.05, which is 1 minus 0.95. So if we run this line, we should see the results of the two-sample t-test. So it gives us lots of information here, some of which is things that we want to look at, and some of which may not be. So we can see at the very bottom that it just tells us what the means are. It tells us what is a 95% confidence interval of the difference of the means. So basically saying that the difference of the means is somewhere between -4 and -30. So one of the groups is between 4 and 30 larger than the other group. And it's giving us our p-value here. So if we're using null hypothesis statistic testing, then we're comparing this p-value to 0.05, and we're saying it's less than 0.05 in this case. So we can reject our null hypothesis in favor of our alternative hypothesis, which is that there is a difference in the means of these two groups. So there is some kind of effect of this educational intervention that we're doing. So again, this is where you can say whether something is statistically significant, but in terms of saying whether something is meaningfully significant, that's where you need to be looking at the confidence interval in terms of thinking of how wide of a confidence interval are you happy with. Might be a bit of a informal way to say it, but what is knowing that this new educational method arrives in an average that's between 4 and 30 points higher than the other original method. Is that enough for you to want to change that method? So it's kind of giving you some advice practically as to whether that's something you want to move towards. Explaining, did you have a question? Yeah. 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 So I'm just going to copy it from here and paste it because I already have it typed up here. But yes, it would basically look like t.test. And then my first one, instead of group 1 score, I would say it's the score variable from my data frame, but only the ones where the group is group 1. And then I would repeat that again, but change group 1 to group 2. And then I would add var.equal an alternative at the end as well. Does that sound okay? And it really depends on how you have your data set up as to how you're going to refer to it. There's lots of literature generally and statistics textbooks explaining how to interpret the p-value and how to interpret confidence intervals. And one thing that I've come across over and over again is that the p-value is the probability of the data, given that the hypothesis is true. So given that our hypothesis of the means being equal is true, the p-value is the probability that the data that we collected is actually true. It's p-value is not the probability that your hypothesis is true, given the data. And I'm not a statistician, and I read this stuff over and over again to try to drill it into my brain, and it's not really natural. Like, I feel like I believe it, but it's not like deep in my heart that so I definitely recommend reading about, reading about how, what the p-value means. There's lots of articles published that do not describe it correctly. So it's a good idea to read some of the ones that talk about how to describe it correctly. There's also quite a few articles like testing grad students and faculty on statements about the p-value, whether it's true or not. And it's just like, everybody fails these tests. You know, people who have been researchers for 30 years are saying that things are correct that are not correct, because it's a pretty complicated topic and a way of thinking about things. So it's a bit of a caveat for me to say that I can tell you things that I've read, but I'm still learning myself and still trying to figure it out. All right. So this was a t-test of comparing our two groups when we have unpaired data, so meaning two different groups that are not related to each other at all. Sometimes you do have paired data. So you might have, for example, your first group might be the baseline, some kind of medical measure, which I won't try to name because I'll get it wrong, but some kind of medical measure, and then they were given some kind of drug, and then you measured this medical level again. And so it's paired because you're the same person before and after. You really want to see what's the difference from the first time you tested something to the second time. And so that is basically running a paired t-test. And it's pretty similar to what we did before, just with adding a component to say that our data is paired. One thing that you can also, that you should also test is that the differences in the scores is normally distributed. So it's a little bit different where before we were looking at, we have two groups, is the data in each group normally distributed? But when we're looking at paired data, we're really looking at the group 2 score or the second score minus the first score, because we want to know how much is something improved or not improved. And so instead of looking at the distribution of the data set, we're looking at the distribution of the differences between the data set. And so there's a couple of ways that we can do that. I'm actually going to skip over it for now, just in the interest of time, but it's basically running the Shapiro test, but for the differences between the data. So you basically need to create a new variable that is the score for the group 2 minus the score for the group 1. So that's assuming that you have them in order. So your 1 to 9 matches up exactly with your 10 to 18 data points. So assuming that we've run that and that the difference is normally distributed, then we can run our t-test again. And I'm actually going to copy the line I have before, just because it's so similar that I don't want to type everything out again. So I'm going to have, and let me just go down a bit so we're not getting confused with all the different ones on here. So I'm going to do t.test for group 1 score, group 2 score. And what I need to say here is paired equals true. Oops, paired equals true. And the other things I can leave as is. So if I run that, I will get a different p-value because we're looking at the differences between the scores in this case. And I'm getting a p-value again that's smaller than my alpha that I set, 0.05. Yeah.
Do we specify that variances equal is true, or is the assumption of the Shapiro? No.
It's not the assumption of the Shapiro. That one's about the normal distribution. Oh. I think it actually doesn't matter in this case because we're only interested in the difference. So if I take this out, I shouldn't see anything different.
Considering that they are the same population, shouldn't the variances be equal?
Not necessarily. That's kind of what we're, like, we don't know whether everyone who takes this drug will improve whatever score it is. But because we're actually only looking at the differences between them, we're only looking at one data set really. And so the variance, we're only looking at one variance. So it actually doesn't matter in this case yet. So I think it just, even though I had it in there, it kind of ignored it because it knows that I'm looking at paired data. So we're getting a similar kind of, I shouldn't say similar, but similar format of showing us the results for the paired test. We're getting a p-value that's saying that we can reject our null hypothesis, which is that there's no difference between the baseline and the score once someone has taken the drug. We're also given a 95% confidence interval, and it's telling us the mean of the differences is minus 17. So basically saying that the score, so I think this is happening partly because, So basically just saying that the score either increased or decreased, we'd have to look at the actual scores for the group, by an average of 17. And so that is something that has worked out to be, the confidence interval around that is minus 32 to minus 3. So again, we need to think about, is that an acceptable kind of band for whatever test or whatever topic it is that we're looking at? So we started with group 1 and group 2. And what we're going to do now is add one more group, group 3. And this is when you might have a situation where you're doing this kind of a test, but where you want to compare 3 different groups. So it might be 3 different soil conditions for growing something, different kinds of medications, lots of different applications. And so we're going to add a group 3 and show how we would do the comparison of the means for that. So we're going to add group 3 score. So again, it's just 9 scores, and it can be whatever it is that we're interested in. So we're looking at 3 different conditions that we're looking to test. So now we have 3 different groups of scores. And so the t-test was for comparing 2 different scores. Did I write 8? Okay, thank you for noticing that. So let me see which one I forgot. I think I wanted to put 76 at the start. So you can add that one in. The groups do not have to be equal size. If they're paired, they have to be equal size because you're looking at before and after. So you need to have the same person or the same condition before and after. If you're comparing different sizes groups, it's okay if they're not the same size, but they're depending on the sizes, there might be things that you need to do to kind of compensate for that. Okay, so what we're going to do now is something very similar to what we did earlier. And so I'm going to copy and paste it. So this is the line that started close to the top after we did group 1 and group 2. We had a line that said my data. So I'm going to copy that line because we're basically doing exactly that same thing, but we're going to add group 3 into it. And so just because that can be a lot of typing, I would rather paste that. So we're starting with my data, and so let's call it my data 2 now because we're creating a new data frame. We're having one variable called group, and I'm going to add in group 3. Group 3 after group 1 and group 2. And then I'm also going to add in where I have my scores, group 1 score, group 2 score, and group 3 score. So if you run that and then just type my data 2 and run that line, you should see 27 entries now within your data frame, and you've got group 1, group 2, and group 3. Is there anyone who does not have that at this point? Just to make sure we're all in the same place. Okay, great. And so now what we're going to do is run a test called Anova, which stands for Analysis of Variance. And it's something that, it's a test that you run that basically will tell you, is there difference between at least 2 of the groups in this situation? So you need to start with at least 3, and it's going to tell you, is there a difference between at least 2 groups? And it won't tell you which group there's differences between, but it's something to run so that, let's say you were comparing 10 different groups, instead of comparing each one individually, which would be, I think, about 50 different comparisons. I might be getting that wrong, but like you'd have to be comparing all of them to each other. You run one big test first to say, are there any differences at all? And if the answer is no, then you're not going to go further and look into the specifics. But it will tell you either, yes, there are differences between some groups, or no. And then we have to take the next step to figure out which groups have differences between them. And so the code is AOV, so analysis of variance. Pretty similar to what we wrote, I think, earlier for one of our, I forget which one now, but we're going to write score tilde squiggly line group, and then data equals my data. And in this case, make sure it's my data too. So that's something that you can just type as is, but another thing you can do is just assign the results of that to a variable. So right at the start of the line, I'm actually just going to type results, Anova, and then assign the right side to that variable. And so when you run it, you actually won't see anything right away. It'll just tell you that it ran that. But then you can add word summary before the variable that you just created. So summary brackets results Anova. And it will then show you the results. And the result that will tell you whether or not there is a difference between at least 2 of the different groups is the p-value here, in terms of comparing it to what you set as your alpha. So if your null hypothesis is that there's no difference between any of the groups, this is basically saying that we can reject that there is difference between at least some of the groups. Yes. I think what happens, let me just run it this way. If you don't do that, I think it presents the results slightly differently and doesn't give you all the information. Let me just do that. So it gives me, it doesn't give me my p-value. I don't necessarily understand why, like why that would be useful to not give that, but it gives me this particular results, which are different kinds of results, not different results. It's giving us the same results, but it's giving us different kinds of values. So, so I think my only good answer to that is just because that's how I've learned it and figured out that this is how you can get the information that you need. Yeah. Yeah.
And it's also a good idea to see that because that's probably variable.
Yeah. Yeah. Yes, those are both very good points. So now we know that because we saw that our p-value is less than 0.05, that there's some differences between them, between at least 2 of them. Yeah. Okay, let me scroll up a bit here. So this is what I saw here. So once I did the summary. Yeah. It's not easy to read all of the results for sure. There's a lot of information presented. And so one thing that you can do, and there's probably multiple ways of doing this, but there's a test you can do. So let me write it out here first. 2p HSD. And if I run that on my results, so this is another reason, I guess, why it's useful to save the result as a variable. What this will actually do is show me a table with the differences between all of the different combinations of groups. And so it'll show you that group 2, the mean is actually 17 points bigger than group 1. For group 3, it's 14 points bigger than group 1. Group 3 is 3 points less than group 2. and then it shows you the probability, an adjusted probability value for each of those groups. And so that can help you then look through and identify which groups have an actually significant difference between the two groups. And the lower and upper here is the 95% confidence interval. So it's really only group 2 and 1 here that have a significant difference, and then like statistically speaking, and then we can look at difference to see whether this is kind of a meaningful number to us. Yeah. Okay. So I'm just looking at the time and it's 7 o'clock. I'm wondering what is the best thing to do if I wanted to cover 10 more minutes. Is that reasonable to keep going, or should we?
Yeah, I think giving the option.
Yes. Okay. Okay, great. So we'll move forward because I do want to show correlation, and we're going to use a different data set for that. It's a data set called IRIS. And let's just take a look at the data set before we get started. So you can type in view, and you have to type it with a capital V, which I often forget. And if you don't, you won't be able to view it. So view IRIS, and it should open up the new tab that shows you. This is a data set that was collected by Fisher back in, I can't remember the date now, I think in the 50s. And it's looking at the length and width of different species, of irises, and looking at petals and sepals. And sepal I had to look up, and I think I have a picture here to show you in case that's useful, just because I'm not a biology person. But it was showing, and even when I look at this, I'm kind of like, oh, it sort of looks the same to me, but I'm sure it makes a lot of sense to the biology folks. But looking at the length and width of the petals of the iris flower, and then there's this other part of the flower called the sepal as well. So that's what these measurements were. And so this table is just showing all of those measurements. So we'll go back to our actual script file that we're writing in. And this is where we can, we're going to just look at the correlations between all of the different variables. So if I just click back here, just to look at, basically, is there a relationship between the length? So let's look at petal, because petal makes more sense to me. Is there a relationship between the length of the petal and the width of the petal? So is that something where there's a strong relationship between the two, where if we knew the length, we could predict what the width is? Or is it something that is so variable that is not actually a useful thing to do? And so we can find the correlation between all of the different variables. And you can do it one variable at a time or two variables at a time, which is a bit time consuming. So instead of doing that, you can basically say correlation of iris, and it will find the correlation between all of the variables. But if we try to run this one just like this, we'll get an error because there is a variable in the iris data set that's not a number, and it doesn't really know what to do with it. And so you could either create a new data frame where you take away that non-numeric one, or you can just use R's convention for choosing specific columns. So in this case, we only want to choose columns 1 to 4, and we want to put square brackets around that. And so therefore, I'll just ignore the 5th column. So if we run that, we should get a table that is sometimes hard to read if it goes on to multiple lines, but it will show you the correlation values between each of the pairs of variables. So for example, and you'll see ones, and the ones are where it's looking at a variable in itself. So that's not a useful thing to look at. But for example, if we look at petal length and petal width, the correlation is 0.96 to 865. So there's a really strong relationship between those two variables. Whereas if we look at this one, for example, the sepal width and the sepal length, there's a negative correlation, and which just means that as one gets bigger, the other one gets smaller, but it's a pretty small correlation. So we're looking at a scale of 0 to 1 for correlation here. So that's just to show us what the correlations are. And we can also create a plot. So when we imported a library earlier called, I think it was called core plot, this is what allows us to create a graphic that can be easier to read. And so you can either copy or just write it on the same line, what we just wrote for the correlation. And I'm going to type in core plot. and then paste what I had earlier for doing the correlation. And then just put a comma and type equals upper. And this is something that I know just through looking through the documentation for how to create a core plot. So again, if you were in the help and you typed in core plot, it would tell you these are the different kinds of plots that you can create. So if you run that, you should get a plot appear that helps you to kind of understand. It looks terrible when you zoom in. Oh, there we go. The relationship between the different variables. So all of the ones on the diagonal, the correlation is 1 exactly. So again, those aren't useful ones to look at. We want to look at the ones that are just above it. And so it's showing us here that if there's a strong positive correlation, it's going to be a dark blue. If there's a strong negative correlation, it'll be red. And then these colors are all in the middle. So it's just a way to view that chart that we were looking at earlier that can be kind of hard to read in a visual way that might be helpful. Yeah.
The colors and like the labels, the score thing on the side gradient, is that built into the
Yes, you can change all of it. Like you can change the text color to be black. You can change like the scale to be different colors. Yeah, and that's what I would find just by going to help and doing core. Was it core.plot? No, core plot. Like you see kind of a scatter plot and then, yeah. And the only reason I didn't do that one this time is that it takes quite a lot of lines of code to create that, that chart. Yeah. Yeah. So yeah, there's like a ton of different properties to that you can change. Yeah. A lot, like, yeah, everything. Okay, and I think that was all I wanted to show for correlation. Really, the main point is that that you're looking at these correlation values, and the correlation values are helping to demonstrate how much of one variable can be explained by another variable. So in the case of petal width and petal length, we see that there's a really strong relationship. So if you knew one of those variables, you could figure out what the other one is. But for some of them, there's not a very strong relationship. The fact that it's negative doesn't mean it's something bad. It just means that it's an inverse relationship. But the magnitude, and there's different levels that are used in different disciplines. So sometimes like 0 to 0.3 might be called moderate, or I can't remember what word is used now. It's kind of like a low correlation, 0.3 to 0.6 might be moderate, and so on. Yep. I think if you run them individually, it will do that. So let me try it, because we just said, show us all of them for all of the variables. I think if I do a correlation test and I specify iris, let's see what happens. $, petal, oops, Peter is not the right word at all. Petal length and iris, $, petal width. In that case, it does give us the individual p-value. I don't know of a way to easily get all of them at once. I know that you can create some visuals, like the one that you mentioned about the kind of scatter plot chart. I believe that one will show it to you. So you can at least get it for one of them at a time. But I'm sure there are ways to do it more efficiently for all of them too. Yeah. 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 And then on the axis, you'll be a histogram of whatever. Yeah. And then the correlation. We'll have the stars for the, yeah. Okay. And then the function is okay. I can't remember if it's that one or another one. I've definitely done those before, and it was quite a few lines of code. Maybe in that one, it might just be one line of code because it's kind of built in, which would be great. Yeah, I think I've done it in the base R way. Okay, that's good to know. All right. Oh. And the one thing that I think we won't have quite enough time to get into, but I'll just give you maybe just the very briefest of how you would do this is looking at regression. And so regression is something that's used when you have when you want to try to explain a variable or to predict the values of a variable. So this is something I've used before, for example, when I had a very large data set that had lots of information about people, including whether or not they had gotten a flu shot. And so I might want to try to predict or explain what are the main factors that contribute to whether someone makes a decision to get a flu shot or not. So does age matter? Does gender matter? Does having been to the doctor in the last 10 years matter? So whatever questions you have. And so it's something that that you can use to try to predict. And the general formula for it, so I'm looking at, there's a data set called MT cars. Let me make sure I got that right. Yeah, MT cars. So it's just information about, I think it's from like a 1972 car book, and it's information about 30 different cars, including like miles per gallon, number of gears, number of carburetors, all that kind of stuff. And so you could use that data set to try to, let's say you wanted to try to predict, can I figure out what the miles per gallon is for a car if I have all of this other information, or how well can I predict that? And so, so the kind of general formula for it is LM for a linear model. And I know that we haven't had a chance to look at this data set, but I'll just say that if we wanted to be able to kind of predict miles per gallon based on the number of gears and the number of carburetors, then we could run this linear model. And again, as we kind of started before for the Anova, I can also assign this to a variable, which I'm going to do in this case, because then I can get more information if I look at a summary of it afterwards. So I'll just run this once just to show you what it looks like without going into a lot of detail. So we can look at the results of a regression analysis, which will show you if you wanted to write an equation to try to explain miles per gallon, your equation would look like miles per gallon equals, good timing, 7.27, that's an intercept, plus 5.57 times the number of gears, minus 2.75 times the number of carburetors. So it's trying to find an equation that can explain a certain variable. Or if you only knew, so let's say you had a new car that was introduced and you only knew the gears and the carburetors, the numbers, could you predict what the miles per gallon would be for that car? And so sometimes a small number of variables can predict that value, and sometimes you need a large number of variables to be able to predict it. And you can see here they give you an R squared value here, and that is something that helps you understand how much of that predictor variable can be explained by those other variables that you have. So in this case, it's giving us a value of 0.72. And I always forget whether I'm supposed to find the square root of it or not when I explain how much of it explains. So that's something to look at. But it gives you your p-value as well, and then your adjusted R squared, and then you can use that to determine whether, as well as the p-values of the individual values, to decide whether this is a good model to explain. So it might also be used for like trying to explain who someone's going to vote for. That would be a slightly different kind of regression because it's a specific, you're looking for, are they going to vote for person A, B, or C versus what is the miles per gallon? Yeah. Yes. I can. I just need to remember how.
The little icon at the top right.
There we go. Okay. Yeah. So that one is basically looking at, so LM for linear model or regression. This is the one we're trying to predict or explain. And then these are the variables that you're trying to use to explain it. So that's really a quick overview just to let you know that it's there. There's lots of other factors to consider, like interaction between your variables. So for example, the number of gears and carburetors might actually be really closely tied together, in which case you may need to include other factors in here to help explain that. But that's as far as I will go now in terms of talking about regression, just because of the time. Are there any questions? Yeah.
Sorry, can you just explain it again? It's miles per gallon by, like
what our results?
Yes.
Summary of the miles per gallon as how it's different from the type of gear.
Right. So let me, I'll write it out here just because, so basically it would look like if from these results you could write an equation that says miles per gallon equals 7.2756 plus 5.5756 times number of gears minus, because it's a minus sign before, 2.7537 times the number of carburetors. Is that the question that you were? Yeah. Is there something left that I? Yeah. Yeah. It definitely didn't describe it in any amount of detail, but yeah, it's kind of. So I don't know if the idea of who someone votes for might be an example, but the idea that, you know, lots of people in general like to be able to predict who is going to win an election, not just based on polls, but based on what they know about the population. And so it's basically looking at, is there actually a relationship between all of the things that we might know about people, like maybe religion might be connected to who someone votes for, maybe age, maybe what area of the country you live in. And so basically regression is trying to see whether there's a kind of an equation that can be written that combines all of these different variables in a way that helps you to predict an outcome, and how well can it help you predict it. So sometimes you get an equation where it'll actually only help explain it in a very tiny way, but sometimes things are so related that you have a very strong relationship. I think probably it's something you might just need to read a little bit about and practice a little bit too. When you see some of it's harder to see once you get past a couple of dimensions, because you can draw a graph of what it looks like for 2 dimensions or even 3 dimensions. Beyond that, it can be a bit hard, but if you have a textbook, it can help explain some of that. Yeah. All right. Well, thank you everyone for coming. And yeah, feel free to ask any other questions at the end if you like to. Thanks.